or something like that, or a true random number generator, you won't be successful. Or when you take data and shuffle it somehow randomly, it also is not natural according to that definition. You have to kind of take it from where it comes from, and that's our physical world. Now, our physical world has some properties, there are two properties I want to exploit in this type of work. It's called information locality and multi-scale similarity. Now, information is transferred by particles in physics. So it actually, if two pieces of data have mutual information, that means they are often somehow nearby. And what's going on here is unlikely related to something that's going on in a different galaxy. And that's because you have to transmit that information. And usually there's no spooky action at a distance. Well, there is, right, if we exclude fancy quantum effects. But usually you have things that are nearby are correlated, and that correlation drops according to a power law as the distance goes larger. And that can be seen in various types of data. On the right, you see, for example, natural image statistics. So if you take photos of basically anything and look how the colors of two pixels are correlated as a function of a distance of the pixels, and you will find out that it decays like a power law, and then this double logarithmic plot, it will become a line. So power laws decay much slower than exponentials, and sometimes the correlation lengths are also infinite even, as opposed to exponential functions. And you see that in all sorts of data, as you see in the graph below. Unfortunately, the text is small, but for example, the critical Ising model, which is a model of ferromagnet, the correlation of these neighboring spins, they decay according to a power law. Then if you take English or French text from Wikipedia and look at the correlation of the letters, they decay as a power law as a function of the distance of the letters. If you take music of Bach, it also decays like a power law, and the human genome as well. So a lot of data exhibit this structure, and in the first part of the talk, I'm going to try to exploit that structure in order to accelerate a practical compression algorithm. And the second assumption is multi-scale similarity, meaning that when you take a data set like an image, for example, and make a low-pass filter over it and scale down the resolution. And if you do those iteratively until you get a very low resolution image, these levels, these scales, have a lot of information about each other. Because at every level, only a bit of information is destroyed. And therefore, if you want to go from low resolution to high resolution, you have to add a little bit of information at every level. And the reason is that microscopic objects are made of microscopic ones, and therefore in physics the information is transmitted to higher levels this way. And this is what I call the quasi-fractal nature of the world. So a fractal is a self-similar structure where you go to finer coarse scales, and the scales there just repeat the same structure on every level. And quasi-fractal means the structure is not repeated exactly, but there's a lot of mutual information between the scales. So, so let's go to part one. We have these power laws, and how shall we exploit them? Well, one way to generate a power law correlated mutual information structure in a data set is to generate the data set using a tree. And the way you can imagine it is, this is what I have derived a couple of years ago. For example, imagine a string of data and at the root of the tree, and then you generate new strings of data, its children, by taking a fraction of the information. You just delete some part of the information and keep just a fraction. And with different children, it's a different part. It's a different fraction, but it's always a fraction. And you do that iteratively until you arrive at the leaves of the tree at a certain height. And clearly, the mutual information between the root and the leaf decays exponentially with the height of the leaf. And that's what you see here. You have an exponential decay. Now the distance between the leaves in the tree is obviously increases with the height of the tree. And that goes exponentially. So you have two exponential functions, and if you solve for the height, you get a power law actually. So there's the double E trick known in the physics of complexity field. So the mutual information between two substrings xi and xj is bounded by the Kolmogorov complexity of QH, which is the complexity of the root, and multiplied by the distance to minus a constant. So, and that's a power law. And so what does it mean? It means that we can generate power law correlated data sets by using trees. And the way you can imagine it is objects nearby often, for example, if two objects stand on the table, right? What do they share? They share the same elevation. If two objects are somehow connected, they have an interface, an informational interface. So meaning that if you know the data describing the interface, then the two objects become independent of each other. And I try to exploit that by representing the interface by these nodes in the split tree, and the object are then the two modules that then are iteratively split as well, because they also depend on substructure. So so what I use is this conditional independence. Suppose we have two modules A and B, like two objects, images of objects, and the whole image X is then reconstructed in some simple way from A and B, let's say by concatenation or by taking a sum. And that conditional independence means that the Kolmogorov complexity of the concatenation AB, given the split or the interface S, it breaks down into a sum. So, and what we assume here is that we have a separable loss function where we have a reconstruction of the image and we have the real image. And the difference between is a loss function, and the loss function should be minimizable for each module independently. And that here is again where our assumption of conditional independence flows into it. If they are conditional independent, then as soon as you know the interface, you can find the minima separately of each other. And you can express that mathematically if the loss function is basically a function of g of f1 and f2, then you can take for g as any strictly monotonically increasing function, and it will be a separable loss function this way. So, let's see how we can derive the time complexity of that kind of split search. So let's say that our data string X consists of one split and two modules, and let's say the Kolmogorov complexity of X is L. And I ask myself then, how many programs do I have to search through in order to arrive at the shortest program? Now, take into account that here the runtime problematic is not taken into account for now. This is all work in progress. That's why I'm just telling you the current state of the of the research. Now I'm just focusing on suppose we have we know the length L of the shortest program. How many programs do we have to search through until we find it? If you do it exhaustively, it's 2 to the power of L. If we do that using this conditional independence assumption, then suppose I is the length of the split, J and K are the lengths of the modules. And then the expression becomes 2 to the I times the sum of 2 to the J plus 2 to the K. And it's the sum because if you search for all, if you have already found the right split, then you can search for the modules independently of each other. Find the minimum here, and then find the minimum there. Due to the separability of the loss function, you don't need to combine them. And that's the crucial part, basically. And at the next step, we exclude degeneracy. We basically assume that the modules are of similar size. So because if one module is much bigger than the other module, then you basically get a degenerate trivial. Well, it's not trivial, but it will contain the full exhaustive case as well. And there's no point in making that assumption if your tree is degenerate. So we assume that the world is structured in such a way that the modules are of comparable size. Maybe they differ by some factor, but it's not like one module contains almost all the information and the other one is not. And we have to still find the physical justification for it, and it would be interesting how it's distributed, but to that topic later. And so if we, for that very simple case, assume that J and K are equal and share, and so their size is basically the remaining length divided by 2. So basically you have a fixed length and of your target program, and you search through all lengths of the interfaces and all interfaces, and then the remaining length you split equally between the modules. That's the way the computation works here. And then you can basically derive that the logarithm of the number of programs that you have to search through is given by this formula here, where IN or IA is the length of the interfaces of the tree. So at each level of the tree you have an interface and it has some length, and those are those lengths. And N is the depth of the tree. So I'm not going to go through the math here, but if you make some rough estimates of how many programs you will have to search through, you will arrive at this formula below, where you see that the number of programs is a polynomial function of the length of the shortest description. So that means if you have a string whose Kolmogorov complexity is L, and if you make the assumption that this shortest description is given by this non-degenerate tree, then you only need polynomial time in order to, or the number of programs that you have to go through is polynomial in L. And that's very good news, because usually it's exponential, right? Maybe I can give you a more intuitive explanation of how it works. Suppose you have a string of length n, and you have to guess it. Then you need 2 to the power of n guesses usually. But what if after the first half you just try to guess the first half, and I tell you when you have guessed it correctly, and after you guessed it correctly, you search the second half. Then you are going to need you're going to be much faster. But what if you can do that recursively? If the second half the first half can be split in 2 halves again, and the second half also in 2 halves. And if you get the feedback that every time, then you actually get polynomial in time complexity. So since that sounds good, I've implemented a little toy example where you have to compress an image consisting of squares, and the squares are on locations where the middle point between the squares is basically the split, and you have a tree of splits, and in the leaves squares are being drawn. And here you see how split search works. You go through all lengths, and for each length you try different split lengths, and for each split length you go through all programs of that length, and then you compute the sizes of the modules, or also try different lengths of the modules. And then this most important part here, these 2 split search calls are in a row behind each other. So you don't have to combine the searches together. You can just find the optimum for one part and then for the other part. And you just find then the minimum, what minimizes the cost, and you return the minimum. And you always find the optimum that way. And you also see that on the right in this double logarithmic plot, you see a polynomial increase in number of steps that you need in order to find the optimal solution. And you see that, for example, for length 60, you need just a couple of million steps, but 2 to the power of 60 would be a much larger number than a couple of million. So, what are currently limitations and open questions? That one thing I have referred to below is how balanced are those modules. So how is the differences between the module size distributed? What's the actual physical motivation? There has to be one. I don't know yet what. And of course, how will the time complexity change, taking this distribution into account? I think it will be a bit more. You will get a bit more complex expression, but if the degenerate case has sufficiently low probability, the polynomial time complexity will remain. That's what my hunch is, what we are going to get. Then generalized to more than 2 modules, of course, this pseudocode and the actual code. And then we have to take into account runtime, deriving a Levin-like search, obviously. And then my goal is to implement everything in Turing complete language for realistic small images. So let's say we can do that for like 16 times 16 pixels. We can do it with all sorts of. We can generate all sorts of images, all sorts of data that way. And then, what shall we do with it? Obviously, for realistic images or realistic data, it will still be too slow, even though we have this polynomial speed up. And that's where the second part comes in, where I want to use the multi-scale similarity. So the assumption again is that when we have a data set or an image, and we coarse grain, we reduce the resolution iteratively, and we have this coarse grain image. then these all scales will be related to each other. They will have big mutual information about each other. So we can find the description of the coarsest one and then add details iteratively. And yeah, for example, if we have an image XR half at the level R, then we take the lower resolution image XR and add some details. That's the way I imagine it could work. However, I don't know yet how much information these two levels contain about each other. So, for example, if PR is the shortest description of XR and PR half is the shortest description of XR half, then it should not be difficult to arrive from one given the other. But how it's distributed, I don't know. And this is some part that should be worked on. But we already know from fractal compression, that's a different part of compression, not developed by me, where people actually use self-similarity. We know that it works well for some types of data. And in my case, in the more general case of quasi-fractal similarity, we have to derive an expression that reflects the mutual information between these scales, not exact similarity. So, but once we have done that, then we can argue, okay, how many programs we'll have to search through in order to arrive at the shortest description of the fine scale data set. Suppose we search exhaustively for the coarse scale, then we need 2 to the power of k of xr. And then for each scale, if we need a polynomial time, then the sum of the polynomials for all scales will also be a polynomial function of the length of the shortest program. So we will be much faster this way as well if we use multi-scale compression. And that doesn't use split search at all. It's all on its own. It would be a polynomial time algorithm. So, but this is a part of the project. It's not worked out in detail yet, as you see. And what I'm planning to do then is to integrate those assumptions, the mutual information locality and the quasi-fractal multi-scale similarity. These are both polynomial time algorithms, and what if I combine them to help each other? That should be even faster then. So the way you can imagine it, take a low resolution image, use split search to find an optimal description for it, or a good description in practice. And then you use multi-scale similarity to make local changes on your program in order to find the next coarser image. And then you make little changes on your program again to arrive at the next coarser image, and so on. In that way, it could be much faster. So, for example, if you have a very coarse-grained image, you can use the first algorithm to divide it into coarse parts, recognize some rough shape of the objects that are in it, and then iteratively proceed. Now, the reason why I'm talking about images and not data in general, it's because it's so easy to imagine, and because it also naturally exhibits those types of assumptions that I'm making, because they come from the real world. But in generally, I'm meaning to hold for various natural data that we derive. If it's like audio or text, these assumptions should hold. And of course you can mess up these correlations, and then nothing will work anymore. But if you refrain from doing so and just take the data as it comes, it should hold more or less. So that's basically what I wanted to say. I have like 2 more slides on a different but kind of sort of related project, just to get some feedback. How much time am I supposed to spend, or do I have 5 more minutes or so?
I was thinking more like 20 minutes, so I do want to leave a little bit of time for discussion. So maybe you could just give a couple minutes overview of the other projects, and then we do Q&A and discussion
Okay,
from there.
just a couple of minutes then.
Yeah, yeah.
Uh, so I have 2 slides anyway. The direction this whole research points to is actually what I might call the algorithmic structure of the universe. So it's at the intersection between physics and algorithmic information theory, physics and computer science. Because we're talking about the structure that the universe or the laws of physics actually install in our data. And it should be an area of physics, but physics is not able to talk about structure because, well, how do we measure structure? And we don't have a better instrument other than Kolmogorov complexity. Well, there are all sorts of attempts, but I think the best thing is Kolmogorov complexity. And the physics usually uses entropy, the Boltzmann entropy, which is simply the logarithm of the number of states of a physical system. And that's obviously doesn't tell you anything about its structure. So, for example, when a physical system cools down into a solid state and all the atoms are on regular positions, physics only says, oh, they're just one possible state, but that the state is regular, it cannot say. So physics is basically impotent in that respect, and it cannot say that structure emerges when systems cool down. And there have been several attempts to alleviate that in recent times, but in general it's difficult. And what I've been talking about interfaces between modules, and how do they occur in physics? You have like a system of particles and then another system of particles, and if they are far away from each other, somehow we can use a force that that is exhibited from one system onto another system, and that force is somehow simple often. And we have on these different scales of description, we have different laws of physics, chemistry, biology, and so on. They have all their own laws. And the question is, how do these laws occur, and how do they become so simple actually? And one thing, I'm not going to dive deeper into it, but what I've managed to derive is that when a system of particles arrives at a regular shape, let's say a sphere when the planet forms, or a snowflake, or a solid state like a crystal. If it's a regular shape, then the force that it exhibits onto the outer world will also be simple. So the Kolmogorov complexity of the mathematical formula actually is limited by the entropy of the system. Um, that's kind of that's this formula below. And I'm not going to go deeper into it, but this project basically embarks on the question how simplicity emerges from the complex interactions of physical particles using statistical physics in combination of Kolmogorov complexity and algorithmic information theory. and I'm very curious about these projects, and there have been attempts in algorithmic thermodynamics, and that's all very curious to me. And yeah, that's all from my side. Thank you for your attention.
Thanks. That was a really great talk. Thanks so much. Um, yeah, I think the algorithmic thermodynamics you're referring to is this paper from Aram Ebteker
Yes,
and
yes.
Marcus et al. I'll just drop this in the chat. If other people are interested. Okay, so I have a ton of questions. I wonder if looks like Roman does as well. Maybe he already has his hand up, so maybe he can go first.
Yes, yes. Yes. I haven't measured the amount of compression. I mean, the algorithm, you mean this in the toy example, it's really not so relevant because it's just a toy example. What I have done here is actually, I so you are completely right in that if you the number of recursion levels and the depth of the tree, if you make it too deep, then it will become suboptimal again. Then because you have lots of splits, you have like lots of nodes of the trees, and you have to search through all combination of the nodes, right? And through all combination of the splits, you have to search through. And if the tree is too deep, then you will not be efficient anymore. And and also, if there is no compression to be found, then there's no point in making a split. It will just become a leaf. So at that point. So does that answer your question? The thing is that making no split is a special case of the search. So for example, I pick a split length, or I have a total remaining length and I pick a split length, and if a split length equals the remaining length, I have no length remained for the modules anymore. So this whole split becomes the whole module.
Great.
Yeah, because the split is a general program. It doesn't mean it splits something. It's a general program, so it can generate the whole thing, whatever you have there.
Actually, there's an interesting connection in compressed circuits. It's kind of finding the minimum circuit size for an arbitrary function or an arbitrary Boolean function. You sort of do a similar binary search over um, the input size or something like that. Yeah, you do sort of a binary search on uh, the input, and then at some level the recursion bottoms out, and you kind of just hard code a table of values. So I wonder if that
Okay.
some connection there.
Okay.
There's this result where you can get circuit size for some arbitrary function, surprisingly. So if you kind of do the naive thing for an arbitrary function, the circuit size is something like 2 to the n. But if you do the this careful kind of trick where you pick the proper level to start your hard coding at, you get 2 to the n over n or something along those lines. So
Okay.
without assuming any structure. So the difference here is, there's several differences here. But okay, any other questions?
Yeah, by the way, I mean, it's not related to the incremental compression. This is something else I've been working on. I can, at some point, I can tell something about it, but just in case people have been wondering. So yeah, more questions, please. Yeah, if anybody has.
Well, I certainly have another question, which is, are you aware of the work from John Wentworth's group on this natural abstractions?
No.
Okay, you guys might have some interesting dialogue because he's looking for similar things where if you have systems that are separated by kind of a large distance or something like that, then their interaction should be sort of the internal details of the object should sort of be screened off, and they should have some more simple interactions. Uh,
Okay.
yeah. So and I guess that's kind of like an abstract description of the object. And he believes that certain concepts sort of form natural abstractions, and hopefully certain things related to human value fall into that category. So that different minds could naturally arrive at similar concepts.
Well, that's a curious thing that we can actually make abstractions, or we can make summaries of paragraphs, we can make abstractions of objects, and
Mhm.
that we arrive at some coarse-grained descriptions that are that can be seen as a sort of interface that the object poses to us, and and the fact that it's possible is a non-trivial thing. You cannot do it with a random string. You cannot derive an abstraction, and also cannot do it with a compressible string that has kind of all its parts shuffled around. And
Yeah.
it is some peculiar property, really, that objects have interfaces, and in physics it's called mean field theory. You use the expression screened off when you have a
Mhm.
bunch of electrons, and every electron uh, has its electric field, but they screen each other off, and from the outside you can take just the mean field of them, and it's a reduced field than the sum of them. So it's kind of a special summary of them, and you get that in physics all the time.
Yeah,
The
this is
screening
exactly the
method.
sort of thing Wentworth's group is interested in. So I sent some link to some summary of their work, but yeah, you
Yes,
guys get into
I'd be
contact with
curious
them.
to know about it. So Wentworth is his
Yeah,
last name.
John Wentworth. I'll type it in as well. He's the main guy for this research agenda. And he's actually at this conference I'm at, so maybe I'll mention your work to him as well. Send me if you have any kind of writing on this direction. I'd love to share it with him.
I haven't published it, but I can
Okay,
write some preliminary kind of
that would
thing,
be great. I mean, this
script.
sometime
Yeah.
before the end of the week, maybe I can bring it to his attention.
What
And
conference are you going?
it's called Iliad. It's an Agent Foundations conference, kind
Okay.
of a mathematical focus. Oh, Gabriel had a question. He had his hand up, so I was gonna call
Yeah,
on him next. Yeah.
yeah, okay. I just wanted to ask, since you mentioned the music of Bach, have you like analyzed his music, or uh, does it have something to do
Whether
with?
I have done it?
Yeah.
No, I'm citing somebody else's works. It's Tegmark's work, actually.
Okay.
Here, Lin and Tegmark, 2016.
Oh yeah.
It's copied from their paper.
Yeah. Cool.
So you can look into it. They've just basically taken a bunch of data and analyze this autocorrelation function.
Okay. Thanks.
Okay, and then Daniel, who actually I've talked to with Daniel a lot about certain related directions. So I think you guys have a lot of mutual interests. So I wonder what he has to say about this.
Yeah. Thank you so much for the talk. It was really interesting. Yeah. So like I think the sort of multi-scale similarity thing is like really similar to the type of concepts in like statistical physics and like renormalization groups and that sort of stuff. And in renormalization groups, like fixed points are sort of like a big thing. Like it's sort of related to critical points and phase transitions. So I was wondering if like the same sort of thing can happen here, where maybe the fixed points, if there is such a thing, has like a similar meaning, or yeah, I was wondering if there's any connections with the multi-scale similarity.
Well, there are many connections. I mean, I had it here on the left side. If you see my slide, mean field theory, phase transitions, the decoupling of timescales often leads to the possibility of decoupling things, like in the Born-Oppenheimer approximation. I mean, if you're a physicist, maybe you're familiar. Renormalization, exactly, you call it. It's a very important thing when studying phase transitions, when studying these types of similarities. I am trying to dive into it and kind of trying to be on both ends, on the algorithmic information theory side and on the physics side, in order to somehow gain insights about the algorithmic structure of the universe. I mean, in my view, it should be a separate research field because it should be a part of physics, because it researches the how our nature is structured. But it's also relevant for AI, because the structure has to be perceived somehow, and we have to find descriptions of this structure. And if we know a priori some things about the structure, then we can build more efficient algorithms. So yeah, do you do research in some of those directions?
I'm currently a master's student at Imperial College London, and so I'm studying applied math. So yeah, I do have like a broad range of interests. So algorithmic information theory is more of a recent interest, and also interested in like physics and just a wide variety of stuff as well.
Okay,
Mechanics, yeah.
sounds great. Sounds great.
Yeah. So that was really interesting. I also think like there's probably like a lot of like algorithmic thermodynamics is definitely a field I want to like learn a lot more about. I do think like so like there's sort of two things, right? Like one is the locality of physics. And I think like the mean field theory assumption is sort of like an additional assumption. So for instance, in easy model, like the mean field approximation is only valid up to a particular dimension. And so it's the case that when you sort of further, in addition to the locality assumption, when you introduce like mean field theories, like you can probably even get like better, more efficient approximations when you try to use like algorithmic information theory for thermodynamics purposes. Is that true, or?
I think so. Well, for example, you mentioned renormalization. When you do the renormalization of the Ising model, for example, then you have the. I mean, for people not familiar with it, it's a model of a ferromagnet where you have, let's say, a 2D plane of spins, which are magnetic needles, so to speak, which can point up or down, and when there's a high temperature, they flip up and down. And when you lower the temperature, then at some point they all look upwards or downwards. And then there's, because they kind of like to align themselves and look into the same direction, and the ferromagnet becomes magnetized. Then there's a critical when the correlation length becomes infinite, and there's kind of structure on all scales. But the way you do renormalization is you define like a block spin. For a block of 3 times 3 spins, you assume that it's kind of one spin, and like if the majority looks up, your macroscopic spin looks up, and if the majority looks down, your macroscopic spin looks down, and you do that iterative coarse graining, and thereby derive how the system behaves on a larger scale. And the way it relates to the algorithmic structure is that, well, who says that the block should be so that the right coarse graining relation should be a block? Maybe it's a line, or it's a circle, or it's some other shape that should be the next coarser shape. And you could, if you have algorithmic structure, you can kind of describe structures that are all on all levels, from microscopic to microscopic, and they can all be different. And if you have the language of algorithmic information, you can actually study the structure instead of just using these very coarse-grained tools of contemporary physics.
Right.
So
So yeah, that's interesting. So like in like traditional statistical physics, like the coarse graining map, like as you apply it iteratively, is the same coarse graining map that you're using for each like coarse grained system. And you're saying that in this algorithmic formulation, you can actually have a different coarse graining map as your like coarse grain
yes,
each of the
yes,
system. That's really
exactly.
interesting.
And
Yeah.
on each level, you can apply a different map, yeah, because the particles might associate themselves not into blocks, but into different shapes. So you should abstract correctly and not just pool over the neighbors in some fixed way.
Right, right. Cool, cool. Thank you. That was really interesting. Cool. Thank you.
I'm happy to, yeah.
Yeah, great. So, a lot of questions. I think if people have more questions, definitely feel free to ask. But I was thinking maybe we open up the discussion for the last 5 minutes or so of the meeting. If anyone has research directions, maybe they want to give a future talk, related ideas, anything like that, this would be a good time. So. Yeah, and thanks a lot, Arthur. That was quite good, very interesting.
You're welcome.
Yeah, one direction I'm sort of thinking maybe for the next one of the future talks would be interesting to reach out to some people in computational cognitive science who do things like program inference and program synthesis. So they already have some of these sort of applied tools to find programs that model things, usually for decision making or inference, but not usually focused on compression, which
Yes.
can have these interesting experimental results in practice, but they don't usually have the same level of kind of theoretical justification as you were kind of suggesting.
Yeah,
But
yeah, yeah.
I'm
They are
trying to get
very
at the temperature of this would be interesting.
yes. It's a large field, and they have interesting algorithms that are made to run very fast because they search through huge numbers of programs, and yeah, you're right, but the theoretical underpinnings are often not so great, and but yeah, maybe that's the trade-off when you want to build something practical and working in practice. It's a result of many years of tweaking, and maybe even when you do computational experiments, and for some reason some tweak works better than another tweak, and then they publish it, and nobody knows why, and but everybody uses it because it somehow works, and these kind of tricks pile onto each other, and I see in those publications like, oh, they use that and use that, and then they use evolution of the evolution of evolvability, something like that. All sorts of different tricks, and then usually they get much faster.
Yeah, another thing actually that your talk makes me think about is whether the reason that a lot of these times these less justified, sort of simplified models that people learn work is because of these high-level abstractions being sort of the fact that usually that often some like details can be kind of effectively screened off.
Yes, I mean that's a very important property of our world. It's often taken for granted, but if you take a random system, let's say you take a bunch of particles, define a bunch of forces between them, and just use the laws of physics to let it run, you often get a chaotic system, and the chaotic system visits every state at some point in time, and well, it can be compressed if you guess the initial program. Let's say that the initial states, but basically that's the way you do pseudo random numbers. Basically, you take a chaotic system like a logistic map or something like that, and you build a pseudo random number generator. So that's something that is basically by definition you cannot get these summaries from them of partial data or something like that. You only can regenerate that number if you guessed it seed or something, yeah. and if you guess the program it's generated by. So it's kind of compressible in a strict sense, but not incrementally compressible, or it's not you cannot think of a procedure that goes step by step and kind of compresses that little part, summarizes here until it iteratively kind of arrives at the shortest program. And these chaotic data sets do not have that property of summarizability, or I don't know how it shall be called. But the world has that. I mean, if the world didn't have that, we would have like just a chaotic sea of elementary particles. That's what we would have. They wouldn't arrange themselves into understandable macroscopic objects. We would have just live in the universe would be just a gas of particles that's kind of chaotically flowing around, and that's it. It would be compressible, yeah, because it's all generated from the Big Bang, from a point and you don't need much information in order to describe it. But it would be compressible, but it wouldn't be kind of incrementally compressible. It wouldn't be understandable step by step. Abstractable, yeah. And so I've been trying to approach this property. How can the world be understandable actually, and how can it be abstractable? And the locality of information plays into that. So that for somehow things that are relevant to understand some part of the world is actually all there. You don't have to look into a distant galaxy in order to understand what's on your table.
Yeah.
And
yeah, it seems right.
Yeah, and
we have a question from Michelle as well. Maybe we should take before we.
Yeah, sure.
I'm gonna have to head out around the one or at the hour mark of the conference, but here.
Yeah, it was a question about the talk, and you mentioned two main approaches. One is the compressing with this kind of tree that splits the information in two parts iteratively, and that's made possible by the locality of the data. And the other approach is through the multi-scale similarity, right? And to me, these two approaches seemed kind of the same thing. They maybe I didn't understand fully what's the difference between these two.
Okay. So the first part, when you describe your image as a tree is where you have in an image, let's say you have two objects that are both standing on the table, and a split would be the elevation of the table that helps you to compute the location of both objects. And so once you know the elevation, the objects can be independent of each other. If they have something else in common, let's say they have a common color or shape, this will also be part of the split. So you have found the elevation, the common color, they are both rectangular, let's say, and you have found that. And apart from that, everything else will be different and independent of each other. So it's not related to some scale where you zoom in or zoom out. It's you have two objects and you have an interface between them, and that's the split. The split is basically the information that you have to know in order to make these objects independent of each other. So
Okay.
it's,
Yeah, I understand, but I was thinking that in a sense, that kind of interface can also appear when you look at the image in a much more coarse-grained way. So if you saw like the blurry image, you would see that there is something underneath, like a table, and some other two objects on it, and from that. From that coarse-grained image, you can kind of infer the same thing. You can have the same interface.
Yes, you can, unless you coarse-grain so far that both objects they are kind of become one.
Yeah.
Then at that point you cannot find it anymore. This interface. So this multi-scale compression is when you have a full description of a coarse-grained description and add some details and find the next the description on the next scale. And the split search is when you find a particular type of little piece of information that via which two objects communicate in an information theoretic sense. So it's the mutual information of two objects. That's the split. When you found that, then you can search for those two objects independently.
It's like the split can connect objects that are that have a higher distance than what the increasing level of details at different scale can do. Maybe.
Can you ask again what higher distance? So maybe I should give another example. Let me think. When you have like hand, you have two fingers, and they have a similar point where they are joined. So when you find the point, then the distance between this point and the one finger is becomes short. So you don't have to describe the positions of those fingers independently when you have some point in the middle. So it's the same reason as when you have clustering. When you find the middle of the cluster, then you have to describe it once, and after that, every cluster point you have a short distance to them. Now, that's the same idea in the information space. So you have basically many points, and they have common information. That's the middle of the cluster, and that's what makes them similar to each other. Similar in the sense that they have a similar position in the clustering sense. In the more general sense, it can be different aspects, like the color of my fingers or the shape is also part of the interface between them. It's everything that two objects have in common is the interface. Has that been a bit clearer, hopefully?
Yes, thank you. I was just wondering if the less or higher level of detail can also be thought of like, for example, displaying an image just with the interfaces instead of describing fully the parts that describing fully the parts that these interfaces connect. So yeah, if we see an image just like, for example, with a description with a caption, or like with a description with the words, with like in natural language, that is a kind of interface also, right? That can
Well, that was something I would call the coarse-grained description. That would be related to the multiscale. So you have like sort of a summary of an image, or some. I mean, a caption is not really a description because it's very lossy. But if you have like of a blurry image, scale down to lower resolution, if you have a perfect description of that, that would be the coarse-grained description.
Yeah, but at the same time, you could have like a description of an image containing two twins. And this is at the same time like a summary of the image, but also an interface between two objects in the image, because you're saying that these people that are in the image are identical. And so
interface is by definition the total mutual information of those two parts.
okay.
So what do these two twins have in common in the image? A lot, right? You can basically, if you have one twin, you can generate the other twin with minor modifications. So maybe they have a slightly different pose of the body or something like that, but they would have a lot of mutual information. So that would be the actual interface. And if you just have some common information about them, then it's not enough to be an interface. For example, if they have both a blue shirt, and if you have not described that in the interface, then the objects are not independent, because if you know that one has a blue shirt, you also know that the other one has a blue shirt. So this becomes not independent. The objects only become independent if you put everything that they have in common into the interface.
Okay.
So then you have to say, okay, we have two objects with a blue shirt, or two people with a blue shirts, and then you have enumerate all the other stuff that they have in common. And then you will get an interface.
Okay. Yeah, I understand. Yeah, with this way of describing it as
Thank you for your question, because I haven't been very clear of what I mean by it. I probably should give more intuitive kind of examples to what I mean by that.
Yeah, thank you for the answer. It was I think it makes it clear for me that it's this information that makes the objects that are interfaced independent between each other, so that having this information you statistically can then make them independent, which is something that the coarse-grained image doesn't do, I guess.
Exactly.
That's clear. Thank you.
Can I ask a quick question?
Sure, go ahead.
I'm not sure I fully understand the split search algorithm, but one thing I'm wondering is, like, to the extent you're making a choice about like what different like parts of the string you're sort of clustering together and like creating interfaces between, is part of the idea that like you want to basically find strings that are like close to one another in like information distance sort of sense, so that you can just kind of describe the cluster like with whatever, you know, the common information is between all of the strings, and then there's like a minimal amount of additional information that is needed to describe each string, or am I misunderstanding the algorithm?
Mm. So, so you mean your question is how do you have like some sort of heuristic of how do you look for the interfaces?
Yeah, I guess that's the idea.
The thing is, when you have if you had already the modules that then you could search for the mutual information and find the interface. The problem is that I have to do it in a reverse way. So I have to find first the interface between something I don't know yet, and then generate it. But it turns out you could just enumerate all programs. you could just enumerate all programs, and for every program, you try to find two modules, and you can search for them in an independent way, assuming that you have picked the right interface. Now, if you haven't picked the right interface, your compression will be suboptimal, and you will get either your loss will not be zero, so you don't reconstruct your actual target image, or you will get a larger program that you need, but this cannot happen because your overall program length will be larger than, and you will have encountered the shortest program already before that, because you enumerate that in a length increasing way. So you enumerate those trees with all those splits, not only in the beginning split, but all sorts of splits that come later. You enumerate them ordered by length. So, and again, with the caveat of runtime excluded. So I don't take into account the runtime of the algorithm. But so if you neglect that for a moment, then if you actually enumerate your programs, your trees by length, then you will encounter definitely the shortest program when you find it. Of course, you won't know that you found it, because there's no way to compute the shortest program, but you will stumble upon it before you stumble upon the longer one. Yeah.
Gotcha. Thanks.
Yeah, thanks for the question. That was a good question.
Can I ask a follow-up question?
Sure, go ahead.
Yeah, thanks. So this is like something that I've been thinking about in the context of like AI alignment, ontology identification, and I think it's like quite similar. So I was wondering, have you ever thought about sort of a similar context where instead of like searching for like the sort of interface between strings, perhaps you have like a hypothesis class, a function class, let's say, and then you have like a probability distribution, some prior over your functions, your hypotheses, and you're trying to find perhaps like some sort of submodules or like function pointers, such that if you have this function pointer, like all of the hypotheses become conditionally independent, and then perhaps like you have a couple of function pointers where like the other hypotheses can like use these function pointers as an oracle, and when they do, like they become conditionally independent. And if you have a couple of these function pointers, you can sort of do this recursively, and you ask the question of like, if I have a couple of these function pointers, can I find another function pointer that make these function pointers conditionally independent? And you sort of have this like recursive substructure. And I think it's like a bit similar. It's just like in a different context. Yeah, I was just wondering if you might be thinking about. So like, I guess the motivation for this is sort of like, if you have like a bunch of hypotheses, like there's one way you can do it, which is like just enumerate all Turing machines, and then like eventually you're going to.
Well, can you clarify what you mean by hypothesis, like in a machine learning sense or in some different
I guess
sense?
in like sort of, let's say you're doing like Solomonov induction, and then you have like just all the Turing machines and weighted by like the Solomonov prior. And then like one way you could do it is by just running all the Turing machines and then see what they produce. Like that's one way to do it. But
Yes.
if there is like, let's say some let's say you can compute a result that's going to be relevant for a lot of the hypotheses, then that way it's like much faster, right? I just have to compute this result, and then like let's say for this hypothesis, I use that result to further compute the sort of predictions specific to that hypothesis, and then for another hypothesis, I compute this result first, and then I use it to compute the result of that particular hypothesis. So it's sort of like a robustly useful sort of submodule that's going to be useful for a wide variety of stuff. And then if you can compute things this way, that's like probably a lot faster than like running like all of the Turing machines like one by one.
You mean you run the Turing machines, and once one stops, that's kind of a result that kind of helps you in the search further in the Solomonoff induction.
Yes, yeah. So like in Solomonoff induction, like you sort of have to run like all Turing machines in parallel to see what result they produce. Now, like and then you could imagine that like maybe like they're sort of repeating computations in some sense. Like maybe there are some computations that they're like running in a redundant way where like you could actually run it once and and it's going to be helpful for a wide variety of all of these results. But because you're enumerating Turing machines, you're actually like running computations over again. Like maybe like you have two Turing machines, two hypotheses that are sort of computing like 1,000 plus something plus like some other number, and then like they're both running that computation, and like if you just run this computation once, and then like you could have just ran this computation once and sort of helped these two Turing machines to help compute the result, but because you're just like running the Turing machines like one by one, they're sort of repeating the calculation in some sense. Whereas if you can find some like redundantly useful substructure, then like you can run this like function once, and then it's going to be helpful. It's going to be easier to compute.
Well, what is compute is in Solomonoff induction is the string that you that you want to
yes
you compute the prior for, and that is the result. And so you don't want to use the result for anything because you already know the result, right? It's that you're looking for programs that compute that result.
yes
So you're asking maybe if I have already found a program that computes the string X, maybe you can use it to find different programs quicker that also compute X. And yeah, I have my doubts that that's possible if you don't make some additional assumptions. Maybe if X has some properties of the kind I have assumed.
yes
I don't know. I haven't thought about it. So in a simple case, if you have, for example, already found a coarse-grained version of X, then it helps you find the finer-grained versions of X. Yeah, that could be. Yeah. I don't know. I have to think about it. Maybe it's possible.
Cool. Yeah. I guess like another like intuition pump there is sort of like your setting is sort of you have like two strings and you have an interface that's sort of induces conditional independence for both strings, and then we're sort of operating in a similar scenario where obviously like each Turing machine it can be expressed as a string, and like the most degenerate case, the simplest case would basically be the same thing where you have a string that you have an interface string that mediates that conditional induces conditional independence between both string representation of the Turing of the program, but then you could imagine that if you like express these things as functions, maybe like the interface is like a sub function that you can call, sort of like an oracle, sort of like something where you can like call the oracle and then produces some result. Then like you could imagine like you have this oracle like function pointer that both Turing machines can call, and then maybe that makes the conditional Kolmogorov complexity of both of these Turing machines a lot shorter. And then something of that sort. So it's sort of like initially you have strings, and then now you have like function pointers or like oracles and that sort of stuff. Obviously you need this same conditional independence to be true to be able to exploit that structure, but it's sort of a similar context, which I do expect to be true. Like I guess like if you think about it intuitively, there when I'm doing like predictions in this universe or just of my observations, there are a lot of hypotheses that I'm running, and I'm not running these hypotheses one by one in its full detail. I'm sort of running some computations that are going to be like useful for a wide variety of hypotheses. And
Yes.
when I sort of observe something, I sort of like, okay, this hypothesis is true, but I'm not going to compute it from the start. I'm just like using the sort of redundantly useful computations that I've already performed and sort of synthesize it a little bit just to get to the particular hypothesis that I'm updating towards. Yeah.
You're kind of collecting a toolbox of things
Yes.
that you can use.
Yes.
That might be useful in the future.
Yes.
Yeah, it has to be. This is all, I think, not possible in general. It has to be some property of our world that enables us to do that, to do this reuse, to find these independencies.
Yes.
Yeah, well, with Solomonov induction, you would have to modify these programs to serve as an oracle and not just as programs that compute the target string.
Yes, or I guess you can sort of imagine a context where like the oracles are sort of functions from observations to some particular output, and in that case, like the oracle like could be the description length could be shorter because you're computing it from the observations.
I mean, you could say, for example, you have seen already a cup, and the next time you want to recognize a cup, you're going to be faster.
Yes.
Because you have it already in memory somehow, and that's also doesn't help you in all generality.
Yes.
But in our world, it does help somehow because
Yes.
things repeat. Yes, definitely, yeah. That's a different part to exploit. I mean, we have a memory for a reason. It's a memory is kind of if you have the space-time of data, not just what we see now, but since birth, what we have seen. If you put it like in a big tensor, and want to compress that, our memory is kind of an attempt to do that compression while the past is not available to us anymore.
Yes.
so we want to approximate the space-time compression using only space.
Yes. Yes.
And then only the current time frame. Yeah.
Yeah.
Because things repeat, we kind of use a memory in order to recall it. So and that's also has a very specific structure that psychologists have uncovered. It's I mean, the further back it goes in time, the less you remember, and also the more the objects that repeat more often in your in your experience, they are they're kept in memory with higher probability, and obviously the emotionally relevant stimuli as well. So you have this heuristic of a memory that probably can be. I mean, if you keep away emotions, that are probably can be somehow formalized how to do that optimally. That would be a specific interesting task. You have to kind of do compression in space-time, but only have this current frame. How to go about this? Yeah. I mean, there are definitely a lot of properties of this world that we can exploit, and And if every of these properties lead to an acceleration of the data compression, what happens if we all combine them together? That could actually lead to real great progress in data compression and in AI in general. I mean, one reason I'm interested in this is to find the actual true in quotation mark the description of object, and not do mere fitting that present day AI is doing. We don't want just to fit some powerful function class to our data. We want to actually find the structure of the data, the correct structure of the data. That the data is probably has been caused by. Yeah, that's why we need it for AI and for the understanding of our world in general.
Yes, definitely. Cool. Thank you. Thank you.
Thank you as well for your questions.
Thank you.
So do we have actually for the next meeting, do we have suggestions? People who want to present something? Mm-hmm. So this telephone theorem is for information transmission between like sender and receiver in the chain or something, or okay, okay. Of the data, you mean? Some subset of the data string, you mean? Okay. Mhm. Ledgers are programs or something, or? Yes, yes. And how is relevance defined? And how is relevance defined? Okay, okay. Yeah, feel free to send it to me. I'm curious to look into it. I mean, it reminds me of the information bottleneck also, how to extract uh, from a string data that is most relevant to you currently, that has the most mutual information to a given different string or something like that. I mean, it wasn't formulated using Kolmogorov complexity, but Shannon entropy. But there's like a line of work doing that. That's also quite interesting in that respect. Yes, sure. I can write it into the chat. There you have it. All right. It feels like our organizers have already left, right? So let me take these links that have been put into the chat so that they don't disappear. Okay, then shall we call it a day?
Thanks a lot. It's very interesting.
All right.
Thank you. Thank you for your
Was
talk.
fun. See you next time. Bye bye.
Bye bye.
Bye bye.